be true, if this is equal to that, I can remove the real operator. I just consider this to be true for both the real and the imaginary part, because this thing is varying rapidly anyhow. So I have an equation where this real operator is removed, and then what happens to the e to the j omega t is common to every term in that equation. It divides out, it can cancel out, okay? And cancel out on both sides. Because now I have removed this real operator. And then the equation, pardon me if I write below this line, the boundary lane, okay? I have this for y is equal to j omega f plus 2f. That is the final equation I have. And then the transfer function, let me write above here, okay? Let me write it over here. So h of omega is y over f, and you can derive y over f from this equation over here, which is just j omega plus 2 divided by j omega plus 4. That is your transfer function. Okay? And you can plot this magnitude and phase, just like you have done for the other transfer functions. Okay, is that clear? Okay? So when you are given an ODE, you can find this transfer function or the frequency response just as easily as you have for circuits. Okay? So are there any questions? No questions. Let's go through some of the properties of the transfer function h of omega for a linear time invariant system. Property of h of omega. Okay? Property 1. H of omega is equal to, if you were to negate the frequency, if you were to make the frequency negative, it is just a complex conjugation of the h of omega. Why is that so? Because when we solve this class of problem, we went through the phasor technique. Okay, we went through the phasor technique. We use this function e to the j omega t and introduce that as a function that causes all things to happen from it. And this function, j and omega always go together. Okay, if you derive derivatives, you derive every other thing, j and omega always happen together. Okay, they always happen together because they started out with a function where j and omega are together. So negating the frequency is the same as negating j. Okay, if you put a negative sign in front of omega, it's the same as putting a negative sign in front of the j. So if you have a very complicated function, like this one over here, okay, you can see that negating omega is the same as negating j, because they always come together as a pair. Okay? So as I told you before, the fastest way to find the conjugate of a complex number is to replace j with minus j. Okay? If you have a very complicated functions of complex numbers, the fastest way to find its complex conjugate is to replace plus j with minus j. Why does that work? Why does that work? Because if you go through the algebra, you trace the algebra. Okay, j would follow your way through. Okay, and if finally you get a Cartesian form. Okay, when you negate j, it's the same as finding the complex conjugation of that number. Okay, so if I negate j, it's the same as negating omega, it's the same as finding the complex conjugation of that function. Okay? Can everybody follow? Okay, Na Yong Lee, can you follow? Okay, good, good. You got 100 in the last test, right? So you should be able to follow. So another thing is that h of minus omega is h of omega. This is true, right? This follows from that. Okay? If you take the magnitude of this, it's the same as taking the magnitude of the right-hand side, but magnitude of a complex conjugation of a number is the same as magnitude of itself. This is the same as magnitude of this is equal to magnitude of this. Magnitude of this is the same as magnitude of that. Why is the magnitude of this the same as the magnitude of that?
There's no contrast. It's just.
Think of it in Cartesian form. If I have a Cartesian form, a plus jb, if this is my h, this will be a minus jb. And you can find the magnitude of this. It's a squared plus b squared square root of. Okay, if you find the magnitude of this, it's also equal to a squared plus b squared square root of. Okay, so magnitude of a complex conjugation of a number is the same as magnitude of that number by itself. If you want to visualize this pictorially in your mind, if you have a complex number on the complex plane called the Argand diagram, okay, if that number is over there, if it has a and b for the imaginary and the real part, if you take the complex conjugation of this complex number, where does it go on this complex plane? If you have this complex number, here, 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 or here. Here, right? It goes below that. Okay? So Z complex conjugation will happen there. You just change its imaginary part. You can see that the magnitude of the line has not changed, only its angle. It just flips around. Okay? And then another property that you should know is that property number 3, the argument. This term is often used, the argument of the frequency response, and the textbook likes to use this angle. Okay, that is not a common symbol. Okay, but this means that. Okay, and that, if you were to change as, if you were to change the frequency, okay, it is negative of the angle of the transfer function or the frequency response with the negative frequency. Why is that so? When you change the frequency, you make a complex conjugation of this transfer function. If you make a complex conjugation of that function, just flip it downward. So the angle becomes the negative of each other. Okay, that property is true. And then you have the last property, which says that at DC, h of 0 is h of conjugation of 0. This property follows from here. Okay, this property follows from here. Okay, but this is special. It says that the number is equal to the conjugation of itself. What does it refer to for that number? The number has to be a real number. Okay, this frequency response has to be real at DC value. Okay, which means that h of 0 is real. It's a real value function. Okay, can everybody see that? I have 5 minutes left. Do you have any questions regarding this? Because I noticed that the amount of time allotted to me to teach a certain section is uneven. Some days I have to teach many examples to you. Some days I only have to teach a few. So I think I better move ahead because I see things cramming up towards Fourier series. I have to go through the book really fast when I teach you Fourier series. So if I go slightly ahead now, I perhaps don't have to go through the book as fast as what is allotted in the timetable over here. Okay? So I'm going to move on to talk about, so these are the property of a linear time invariant system. Okay? And remember that the frequency response is just the ratio of the input phasor, the output phasor to the input phasor. And phasor is very important here. Okay? So if I give you an example, like example 5.5 of the textbook, okay? That if I give you the fact that the transfer function or the frequency response of the system is given by this thing over here, okay? And if I give you something that there are two inputs to this system, okay? There are just two inputs to this system, and they call this system h of omega, and it's a linear time invariant system. Okay, if I have an input to this system f of omega, okay, maybe I have an output y of omega coming out. I don't know if they use y, but I guess they use y as the output, okay? So if I give you the fact that there are two inputs, one input is at this value, another input is at this value, cosine of 2t plus pi over 4, okay, or 45 degrees. How would you find the output if given the fact that these are the two inputs? Yes, Larry?
Does that say 0 times 5t?
0.5t. Okay, this is omega. This is omega. Okay, omega equals 0.5. That's what I mean. Okay, at least that's what the textbook means. Okay? How would I find the output of this system? What must you do first? You use the principle of linear superposition and convert this into phasors. Okay, what is the phasor rep of this thing? Minus 2j. That's it, right? But remember that this is at omega equals to 0.5. And what is the phasor rep of this? E to the j pi over 4. And this phasor is at omega equals to 2. Those are the two distinguishing features. Okay? So if these are the phasor input, phasor output for frequency 1, omega 0.5, what is that value, y1 at omega equals 0.5? It will be the phasor input minus 2j times the frequency response at omega equals what? What must I pick for my transfer function or frequency response over there in order to make the output come out correct? 0.5. Okay, this has to be evaluated at omega equal to 0.5. Y2 at omega equals 2 would be the input phasor, e to the minus or plus j pi over 4, times the frequency response, but what frequency must I evaluate it at? 2. Okay? And you can plug in those values, get these two phasor output, and what must I do to convert them back to the time domain? I multiply by e to the j omega 1t for one case, e to the j omega 2t for the other case. Here I pick omega equal to 0.5, here I pick omega equals to 2. And then I take the real part, and then I get back that thing in the time domain. Okay? So we stop here.